Welcome all. For today, our topic is pipelining. What is pipelining? It is a technique in which we decompose a sequential process into sub operations. So we have a process, and the process is such that it is possible that it can be decomposed into various sequential parts, and in this we decompose, and then each sub-process is executed in a special dedicated segment, and this happens concurrently. So if I have a uh, process, we decompose it into parts, and there are many segments in the system. So one segment is processing something, the another segment is not idle, it is also processing another thing, and each segment is busy with some new job, and making sure that each segment becomes useful, and the processing speed also increases by this. So this pipelining is actually a concept which we use for uh, increasing the speed or decreasing the time of operation of a computer. So the whole circuitry will be divided into segments, and the result that is obtained in one segment is passed to the other segment, then the result of the second segment is passed to the third segment, and so on, and the final result will be obtained from the last segment when the all the segments have operated on that particular data in some way. Finally we will get a result. So the final result is obtained only when the data has passed through all the segments. And how is this overlapping of computation made possible? It is made possible by introducing registers between segments. So if the first segment is doing some operation, it will put the result in the output register, and then it can start a new operation, and the next segment will take its input from the output register of the first segment, and this will move on like that. To understand it properly, we can take an example. So here is an example that I have to perform this operation A into B plus C, but we have multiple numbers for which we have to do this. So here this is I runs from 1 to 7. So first I have to do A1 into B1 plus C1. This is one operation. Then I have to do another operation, that is A2 into B2 plus C2, then A3 into B3 plus C3 up to 7, A7. So in total, we have 7 operations that are to be performed on different numbers. In such a for such operations, we can use the concept of pipelining, which will make the system more efficient, and the processing time will decrease. The total processing time of all these 7 operations will be less. How will that happen? Let us first see here that what will the processor do when it has to do this operation. First, it will transfer the first number into some register, let us say R1 register. Then the second number will be transferred to another register, R2 register. These registers are the registers of CPU. So this operation, this thing we call as input. So we are inputting the values and we are putting them into registers. Then In the next step, we will do the multiplication, because multiplication has a higher priority than addition, so it should be the multiplication. We will do R1 into R2 and then store the result in some other register, say R3. At the same time, we will take this C, we will put it in R4. So the second uh, set will be the multiplication and this inputting of C. And this is the second set of operations. Then at the third set, or the what we will call as uh, this register transfer operation, and here we are adding two registers. So this is in one register R3, this is in R4. Now we have to add them simply. So R3 plus R4 is stored in R5. So we are done here, and this whole process is to be repeated 7 times, because I runs from 1 to 7. Now what will be the circuit for this? It will be this circuit, which we can see on this side. So we have two registers, A1 will go to R1, B1 will go to R2. Then this is done. Then in the next next clock cycle, what will happen? So the first clock pulse will come and this operation will happen. In the second clock pulse, here we can see the multiplication will be done. So R1 and R2 will be multiplied and answer will be stored in R3, and simultaneously C1 will be put in R4. Done. And in the third clock pulse, this operation will happen, that is R3 and R4 will be added and put to R5. So for doing this operation, the circuit would be somewhat like this. And if we see keenly, this is a typical pipe. This is a pipelining circuit. How? Because when initially this will be A1, B1, they will be put here. Then this A1 and B1 will be multiplied. When this multiplication will happen, at the same time, A2 and B2 will come here. So parallelly two things are happening. When the multiplication of A1 and B1 will be occurring, this we will make sure that this part doesn't remain idle. At the same time, we will do the reading of this A2 and B2. In the next clock pulse, we will have A1 into B1 here and C1 here. We will do the addition, but we will make sure that this part doesn't remain idle. So when addition is happening of the first I equal to 1, at the same time for A2 and B2 multiplication will be happening, and at the same time for A3 and B3 the reading will be happening. So in the third clock pulse, here A1 into B1 plus C1 will be happening. Here A2 into B2 will be happening, and here A3 and B3 will be getting stored into these two registers. So since this is happening this way, this we call as pipelining. Why this name has been given? Because this concept is similar to that of a industry segment pipeline, industry assembly line, not segment, in industry assembly line. If we look at an industry assembling line, it has many segments and things happen like that. Some assembly has been done in the first segment, then it is moved to second level of assembly. At that time, the first segment doesn't remain idle, it takes another job for assembly purposes. So this way we optimize things. And to create this pipeline, we need to put the circuit in a certain way and use intermediate registers. So this is a simple example telling us what a pipeline is. Now if I put all these operations that will occur here for I equal to 1 to 7 in a table, the table would be somewhat like this. So let us first see what segments are there in this pipe. There are 3 segments. The first, based on this here, there will be 3 segments. In the first segment this will happen, in the second this will happen, and in the third this will happen. So in the first segment, this constitutes the first segment, this will be the second segment, and this will be the third segment. So we can say there are 3 segments in this pipe. So we can write here in the table segment 1, segment 2, segment 3. In segment 1 we have registers, these R1 and R2. In segment 2 we have R3 and R4, and in segment 3 we have R5 register. And let us put clock pulses from here. So in the first clock pulse, what will happen? First clock pulse means that for I equal to 1. So let us say everything is empty here and the clock pulses have started. Now the first number is being calculated. So the at first place A1 will come here and B1 will come here, and no other operation will happen. So that is what we are saying. In the first clock pulse, segment 1, in A1 will go to R1, B1 will go to R2, and all other are empty. In the next clock pulse, these two will be multiplied and put to R3. So A1 and B1 will be multiplied and put into R3 in the second clock pulse. But at the same time, because we are using the pipelining concept, A2 and B2 will come here. So A2 and B2 will come into R1 and R2 respectively. Fine. And when this will be multiplied, the answer will be stored in R3. So multiplication answer is in R3. At the same time, we know that C1 will be transferred to R4, this thing. So C1 will be transferred to R4, and this will be empty, this R5. In the third clock pulse, this adding will be happening on I equal to 1. Multiplication will be happening on I equal to 2, and this transfer will be happening on I equal to 3. So that is what we are showing here in the table, that at the third clock pulse, this will be happening, this adding and multiplication for A2, fine, and transfer for A3 in the third clock pulse. In the fourth clock pulse, A4 will be transferred to R1 and R2, A3 and B3 will be multiplied in multiplier, and C3 will be transferred to R4, and the addition will be happening for 2. Fine. And this way we can continue. In the seventh clock pulse, A7, B7 will come, 6 will be in the multiplication segment, and 5 will be in the addition segment. Good. Now, since after 7 we don't have any new entry, if there would have been a new entry, we would have put it here. So it implies that 7, we don't have an 8 here. So here in the first segment, there will be nothing will be happening. In the second, A7 will be operating, I equal to 7 will be operating, and in the third, 6 will be operating. And in the next, these will be empty because we don't have a new entry, and 7 will be operating in here. And we will get the result here for I equal to 7. So we are done. And if we look keenly here, the result of I equal to 1, that is A1 into B1 plus C1, is produced here in here, fine. In the third clock pulse, this is produced, and we know that here the number of segments is also 3. So we can easily say that it takes 3 segments. For a 3 segment pipeline, it takes 3 clock pulses to get the first answer. So what we deduce from here, that if I have a 3 segment pipeline, the first answer will be produced after 3 clock pulses. If I have an n segment pipeline, the first answer will be produced after n clock pulses. And second answer is here, it is produced in the 4th clock pulse, third in the 5th clock pulse, fourth answer in the 6th clock pulse, and so on. The 7th answer is produced in the 9th clock pulse. Now let us look at a general structure of a pipeline. So a general structure is this. This is a simple block diagram type structure. So we say that this is a 4 segment pipeline. So obviously there will be 4 boxes, S1, S2, S3 and S4. And to make sure that it works as a pipe, and we put resistors in between. There may be one or multiple resistors. So this is a general structure of a 4 segment pipeline, and obviously there will be a clock pulse going to each segment, each resistor. In pipelining, there is something called a space-time diagram. What is that? It is a diagram in which on x-axis we put this clock cycles, and on y-axis we put the segments. So this is space-time diagram. So space and time we are plotting in this table. So these are the clock pulses that will go in the computer, in the processor. So this is one means the first clock pulse, second, third, fourth, and so on. And from here we are putting the number of segments. Since in this diagram there are 4 segments, so we write 1, 2, 3, 4 segments. And clock pulses, we don't know. Let us see how many clock pulses it will take to execute certain thing. Here for constructing this table, we are supposing that we have 6 tasks at hand. That in total we have to perform 6 operations, so which we typically call as task. So we have 6 tasks: T1, T2, T3, T4, T5, and T6. So the processor begins to do the operation. What will happen? First, it will take task 1 in the first clock cycle. In the first clock cycle, it will take task 1. The task 1 will obviously first go to from here to S1, the segment 1. Done. Nothing in other segments right now. In the second clock pulse, this will move to the segment 2. The first task will move to segment 2. At the same time, segment 1 will not remain idle. It will take another task, T2. So in second clock cycle, the segment 1 will not remain idle. It will take another task, T2, and the T1 task will reach to segment 2. In the third clock pulse, what will happen? This S2 thing is done. Now the first task will reach to segment 3. So in the third clock pulse, the first task has reached to segment 3. And at the same time, these will not remain idle. The second task will reach to segment 2, and a new task, the T3, will come into S1. So in the third clock cycle, 3 things will happen. T1 will reach segment 3, T2 will reach segment 2, and T3 will reach segment 1. And this process will continue because we have only 6 tasks. So in the 6th clock cycle, T6 will reach S1, and here it will be in segment 2 we will have T5, in segment 3 we will have T4, and in segment 4 we will have T3. Now in the 7th clock pulse, there will be no new entry because we have only 6 tasks. Had we had if we had another task here, it would have been T7. So we had only 6 tasks, so there will be no new fetching. So there will be nothing in segment 1, but in 2 there will be 6. In segment 3, T5 will be there. In segment 4, T4 will be there, and so on. Finally, we will see that T6 will come here to segment 4. When T6 reaches here, segment 4, it will produce certain output, and all is done. All T1 to T6 tasks have been done. So we don't need to go to another clock cycle. So this way, this table tells us that 6 tasks in a 4 segment pipeline will be completed in 9 clock cycles. Fine. So we have in 6 tasks in a 4 segment pipeline will be completed in 9 clock cycles. Likewise, we can take any example, any number of segments, any number of tasks, and see how in how many clock cycles that will be done by just drawing this table. Let us take up a numerical problem. The question says that if we have a non-pipeline unit, so if I have a traditional processor, it has a non-pipeline processing, and it is given that it takes this much time, Tn nanoseconds, to process each task. So for one task, it takes Tn nanoseconds to process it. What will be the time taken by it to process n tasks? How much time it will take to process n tasks? This is very simple. If one task takes Tn time, n tasks will take n into Tn time. So this is very simple, A part. Now B part says that if I have a k segment pipeline, so I have another processor which uses pipelining, and the pipeline is a k segment pipeline, means that the pipe has k number of segments in it, and it is given that the clock cycle time is Tp nanoseconds. So this Tp is not the time to process a task, it is the time of one clock cycle. So one clock cycle is of Tp nanoseconds. Okay, what will be the time taken by it to process the same n tasks? So we have again the same n tasks as in part A, but what will be the time in this? This system is different because this is a pipelining system. This was a non-pipeline unit. So let us see what will be the answer. First, it is given that segments in this pipe are k, okay, and if there are k segments in the pipe, what will be the time taken to complete the first task? We just saw that in the previous example also, that if we have here, we can see it here, that we had 3 segments. First task was completed in 3 clock cycles. Fine. Here we had 4 segments. The first task was completed in 4 clock cycles. Here T1 was completed in 4 clock cycles. So that means if there are k segments, the first task will always be completed in k clock cycles. So since segments in the pipe are k, that means the first task will complete in k clock cycles. Okay, what about other tasks? The second task will complete in, it will complete only in 1 clock cycle. Why? Here we can see it. T1 completed in 4 clock cycles. It took 4 cycles, but just after 1 clock cycle we got the T2 answer. Just after 1 clock cycle we got the T3 answer. So all other tasks complete in just 1 clock cycle. That means each of the remaining n minus 1 tasks, total tasks were n given in the question, The first was completed in k clock cycles, and the remaining n minus 1, each of them will be completed in 1 clock cycle. Now, so how many clock cycles in total will be that? For n minus 1 tasks, it will be n minus 1 clock cycles. So again, we can see it from here. T1 was completed in 4 clock cycles, okay. T2 in 1 clock cycle, T3 in the next clock cycle, T3, T4 in the next. So for this 1 clock cycle, for this 1, 1 and 1, which makes 5 clock cycles. 5 means n minus 1. N is the number of tasks. Number of tasks were 6, so this is 5. So that means the remaining n minus 1 tasks will be completed in n minus 1 clock cycles. Okay. So done. Now what will be the total time taken by the pipeline to complete n tasks? For first task it is k clock cycles. For the remaining tasks it is n minus 1 clock cycles. So we add them up, it will be k plus n minus 1 clock cycles. And what is 1 clock cycle? That is also given in the question. 1 clock cycle is TP nanoseconds. So 1 clock cycle is TP nanoseconds. So the final answer we get that the total time taken by n tasks to complete in a k segment pipeline is this much. Okay, now the third C part says, what is the speed up of the second system over the first? What is the speed up? How much faster is the second system, this pipeline system, than this non-pipeline system? Very simple, we can do this by finding the ratio of the two. So the time taken by this divided by the time taken by this, so that will be the speed up. So speed up will be, so the answer of the A part divided by the answer of the B part. So first part was n into Tn, second part was k plus n minus 1 into Tp. So this will be the speed up. The number of times the pipeline system is faster than the non-pipeline system, that will be given by this formula. So we are done with the numerical, but what we learned from this numerical problem is that the speed up of a pipeline processing over equivalent non-pipeline processing is given by this formula, where n is the number of tasks, Tn is the time taken to complete one task in a non-pipeline system, K is the number of segments in the pipeline system, Tp is the time for one clock pulse. So this is a very important formula and must be remembered. Okay, we can for generalizing purposes, simplification purposes, we can say that we can do some more calculations. We can say that when the number of tasks will be very high. So if the number of tasks that the processor is operating on are very large, so if n is very large, that means k and 1 can be neglected, right? If n is very large, because k will always be small, number of segments cannot be in millions, so number of segments will always be less. 1 is a small number, so if n is very large, what will happen? This formula will become Tn by Tp. K and 1 can be neglected, and this formula will be converted to Tn by Tp. And again, we can, if we assume that the time taken to process a task in pipeline system is same as that in a non-pipeline system to process one task, if we assume that it is same, then we can replace Tn by KTP. Fine. So the answer will be K. So what does this thing mean? Speed up is K. In this, after making this assumption that n is large and this is same, uh, this has a meaning. What is the meaning? It means that the theoretical maximum speed up that a pipeline can provide is K. That is the number of segments in the pipeline. So the theoretically the maximum speed up that any pipeline can give us will be equal to the number of segments in the pipeline. So if a pipeline has 10 segments, the maximum speed up, theoretically the maximum speed up will be 10. So it will be 10 times faster than the non-pipeline system. And it can never exceed this figure of 10, this figure of K.